Hello everyone. In this video, we will be discussing about the direct comparison test, which is an important test to check whether a particular infinite series converges or diverges. So in this topic, what we have to do, we have to figure out whether a particular given series converges or diverges. So as the name indicate, direct comparison test. So one of the series will be given to us. Let's say this is an goes from 1 to infinity, and we have to compare this given series with another series which we will denote it by bn. Now we have to assume this series on our own, and we have to assume in such a way that we should know its nature. So you know that its nature should be known. Like you should know whether this particular series converges or diverges. You have to assume in such a way. And then we have to compare both of them, which one is greater, which one is smaller, and depending upon that we are going to decide whether the an converges or diverges. So what happens over here is, so first of all you can see the an is given to us. This is the given series and this is the assumed series, and both of them should have the positive term, that is the first condition. Now these are the rules over here. If bn converges, if the which we have assumed the series this converges and an is less than equal to bn, then an also converges. What does that mean? So let's understand with the help of this. First of all, when we are saying converges, so we will draw the diagram of the series like this, and like this. This means that it is converging. Converging means coming to an end. It is converging to a particular value. This diagram indicate converges, and if we are drawing like this, it means it is expanding, expanding, expanding. So this is known as the concept of diverges. So this series diverges and this series converges. Diagrammatically we will show like this. Now what we will say, suppose we have a given series an is given to us and bn we have assumed, and let us say we know an is less than bn, and we also know, let's say this series converges. So just draw the diagram. If bn converges and bn is greater, converges means the diagram of bn will be like this. This is the diagram for bn. Now since an is less than bn means an series will lie inside these two lines. It will always lie inside this. So what is the possibility for an? An cannot go away from this. It will always lie inside this. So the only possibility for an is that it has to pass through this bottleneck. So it means the an also converges. But on the other hand, if we are having an is less than bn and we know bn diverges, the greater one is diverging. Now the greater one is diverging. Greater one means which we will draw outside. So this is bn. Bn is diverging. Now an is inside these two lines. If an is inside these two lines, so an has two possibilities. An can go like this, or an can go like this. So it could be an or it could be an. An can expand or an can converge. So in this way we cannot say converging, converges or diverges. So you can say in this case the test fails. We cannot comment upon the an. It can be diverging, it can be converging also. So this is the first case, right? In the second case you can say the test fails over here. In this case we can say an converges. On the other hand, sometimes you will be having an is greater than bn, and let's say again the same case. If bn converges, the given series converges and bn is less than this time. So bn converges means we will draw the diagram for bn like this. It is converging. An is greater than bn. Greater than bn means it will lie outside these two lines. Now if it is lying outside these two lines, so an has two possibilities. It can go like this. An can expand, or an can go like this also. Both the possibilities are an for there. This is also an and this is also an. So it can converge, it can diverge also. So in this case we can say the test fails. We cannot comment upon the an. But on the other hand, an greater than bn and we know that bn diverges. The smaller one is diverging. Smaller one diverging means it is going like this. This is your bn. This is diverging. Now an is greater than bn. It is lying outside of this. So since it is lying outside of this, so only possibility for an is that it has to go like this only. It cannot cross the lines for bn, right? It cannot go inside this because all the terms are greater than bn. So only possibility for an is to diverge. So here we will say an diverges. So these are the four possible cases we will be having to compare the series. So that's what written over here. You can see if larger series is finite, the smaller one must be finite. It means the larger series is converging, the smaller series also converges. You can see the larger series converges in the first case, the smaller also converges. And similarly, if the smaller series diverges, the larger one must be diverging. In this case, if the smaller series is diverging, the larger must be diverging. In rest two cases, the test fails. So let's understand with the help of an example. So it is written, determine whether the series converges or diverges. So let us compare. Now for comparison, we will be taking a very smaller one in which we should already know the nature of this. So here, what is an? An is 1 upon 2 power n plus n. Let us say, let bn is equal to, now whenever you are comparing, just try to remove some of the terms. Let's say I am removing this n over here, n being a positive number from 1 to infinity. Let's say I am removing this n. So I am keeping it only 1 by 2 power n. Now 1 by 2 power n I already know. That's a geometric series. And what is the common ratio? It's 1 by 2. And when the common ratio is 1 by 2, what happens in this? Since absolute value of r is less than 1, therefore it converges. So I know this geometric series converges. Now I have to compare both of them. Which one is greater, which one is smaller? So you can write like this, 1 upon 2 power n plus 1, and this is 1 upon 2 power n. In both of them, the numerator is same. In the denominator for an is larger. If the denominator is larger, it means that complete fraction will be smaller. So it means this is greater. So bn is greater, and we know that bn converges. Right? So if the greater one is converging, the first case, the greater one is converging, so only possibility for the smaller one has to converge only. Or you can draw the diagram over here. The greater one converges. This is your bn. So what is the possibility for an? An is smaller one, so an has to pass through this bottleneck. So an also converges. Therefore, an converges. That is how we can compare. Let's take the another example. Here also we need to compare whether the series converges or diverges. So in this case, what is our an? 1 upon n square plus n plus 1. And let us say the bn I am assuming, just remove this n plus 1. So only 1 by n square is there. So just like this, it is 1 by n square. Now which type of series is this? That's a p series. And in the p series, what is the condition? The p means the exponent of this n is the p. So here p is equal to 2, which is greater than 1. If p is greater than 1, it converges. Is less than or equal to 1, it diverges. So therefore, by the p series test, we know it converges. The bn converges. Now let us compare both of them. N square plus n plus 1. This is 1 by n square. Directly we can see that the denominator of the left hand side is larger. If the denominator is larger, so this complete fraction is smaller. So again, just like the previous case, the larger one, what happens to the larger one? It converges. If the larger one is converging, so definitely the smaller one has to converge. So you can say also converges. You don't have to remember the result, just draw the diagram. Larger one converges, so smaller one will also converge. So we can say this particular series converges. Let us take one more example. Here also we have to comment whether it converges or diverges. So let us say our an. What is our an? N square upon n cube minus 3. And when we have to assume the bn, try to remove some of the terms. Let's say I am removing this constant. Whenever the constant is present, remove the constants first. So if I remove this constant, I will be left with n square by n cube, and I know its nature. So if I remove the n minus 3, so it will be n square by n cube. We can make it simple a little bit. This is 1 by n. It's a harmonic series, or you can say also a p series. It's a p series. What is the value of p? 1. So when the value of p is 1, since p is less than or equal to 1, therefore it diverges. According to the p series test, the p is the exponent of n, and it is 1. When the p is less than or equal to 1, it diverges. And now let's compare which one is greater, which one is smaller. So if you want to compare, you can compare like this. let's make it like n square by n cube. So the numerator for both of them is same. Now in the denominator of the left hand side is smaller. If the denominator is smaller, then complete fraction will be larger. So this is greater, right? Now in this case, we are having the smaller one diverges. We know the smaller one is diverging. So if the smaller one is diverging, so let's draw the diagram like this. This is the diverging nature for the Bn, and An is greater than that. If An is greater than that, so and what is the possibility for An? If the smaller one is diverging, so only possibility for An is to diverge only. So therefore it diverges. I hope you have understood the concept of this thing. By comparing, you just have to assume a Bn with a known terms, and you should know its nature already, and just by drawing this diagram you can easily compare which one is diverging and which one is converging, or whether the test fails or not. So if you like this video, please subscribe to the channel, and if you have any doubt related to the AP calculus, connect with me on this WhatsApp number. Thank you for watching this.